Good morning, good afternoon. From the International Society in Quantization, Geometry and Dynamics, ISQGD, Advancing Mathematics from K-12 Education to Higher Research. It is a pleasure to introduce today's ISQGD distinguished speaker, Dr. Zhiqiang Wang, a young mathematician whose research focuses on the rich and rapidly developing field of fractal geometry. Dr. Wang is currently a postdoctoral fellow at the University of British Columbia, Canada, and has also been affiliated with Chongqing University in China. Dr. Wang received his PhD in mathematics in 2024 from East China Normal University. Following the completion of his doctoral studies, he worked as an assistant research fellow at Chongqing University before beginning his current postdoctoral research at the University of British Columbia. His work lies within fractal geometry and related areas of geometric analysis, where he studies the structure and dimensional properties of fractal sets and measures. In recognition of his early research achievements, Dr. Wang was awarded the Zhongchaqing Mathematics Award by the Chinese Mathematical Society in 2022, one of the notable honors for young mathematicians in China. His research contributes to the ongoing development of modern fractal geometry and connects with broader themes in geometric measure theory and dynamical systems. We are delighted to welcome Dr. Zhiqiang Wang to the ISQG Distinguished Lecture Series, and we look forward to his presentation and the stimulating discussion it will inspire. Please join us in warmly welcoming Dr. Zhiqiang Wang to the ISQG Distinguished Lecture Series. Yeah. Okay,
Can
now we can
you
see. Yes,
see
now we can see.
my screen?
Yes,
Okay.
now we can see the screen. Yes, good.
Okay. Thanks the introduction by Marina, and thanks the invitation. And it's my pleasure to give a talk here. And today, I will talk about spectral eigenvalue problem for self-similar spectral measures. First, we will start with the definition of the spectral measure. Here, given a vector lambda, and we let e lambda x donate the function e to the power 2 pi I lambda dot x. Then we given a Fourier probability measure mu, and then we consider the square integrable function system function space L2. If a measure mu is called a spectral measure, if we can find a subset lambda such that the functions e lambda for all lambda in capital lambda, this family forms an orthogonal basis for L2, and the set lambda is called a spectrum, and the pair mu and the lambda is called a spectral pair. For example, we know that the Lebesgue measure on the cube, the Lebesgue measure on the cube and the integer lattice is a spectral pair. And the studies of the spectral measure dates back to the Fugit spectral set conjecture. It says that if gamma is a measurable subset with positive and finite Lebesgue measure, The gamma is a spectral set. In our notation is that the normalized Lebesgue measure on gamma is a spectral measure. If and only if the set gamma can tell the whole space by translations. This is the spectral set conjecture. In 2004, Terence Tall gives the first counterexample for this conjecture for d is larger than 5. After that, the both direction have been disproved for d larger than 3. But now this conjecture remains open for d equal to 1 or d equal to 2. Recently, it has been shown that these conjectures hold for all convex bodies in all dimensions. Here, convex body means that a compact convex set with a non-ampered interior. Um, Here, I will not go into more details about this conjecture. Um, we will focus on singularly uh, singularly continuous spectrum measure in our talks. Before that, we remark a theory says that the spectrum measure have a pure type law. It says that if a spectrum measure is compactly supported, then we know that the mu must be one of the three pure types. It means that the measure mu must be either discrete and the support is finite, or the mu is absolutely continuous, or or the mu is singularly continuous. If the mu is absolutely continuous, then the study of spectrum measure will reduce to the spectrum set conjecture. So in this talk, we will focus on the case that mu is a singularly continuous measure. So next, we will introduce the self-similar set and the self-similar measure. In our setting, let capital N be an integer and the set D is a finite subset. We only consider the case in one dimensional. So here, D is a subset of real numbers. Then there is a iterated function system generated by n and set d. Here, the function phi d is the x plus d over n. Um, if we have this iterated function system, there is a theorem says that there exists a unique non-ampered compact set K, which is the environment. The set K is called a self-similar set. The environment means that the set K is the union of if the union of the phi dk for d in D. This means that the set K is the union of the small pieces which is similar with the set K. In our setting here, the set K can be written as the sum of the dk over nk, where the dk from the set D for every k. And also for this iterated function system, there exists a unique Fourier probability measure mu, which is the environment. This measure is called a self-similar measure. The environment means that the measure mu is the average of the push-forward measure of phi d. So the measure mu, in some things, the measure mu is the in some things is a union of the small copies, which is self similar with the mu. Here, in our setting, the self-similar measure mu have an infinite convolution structure. For this, we define for a finite set A, we define the measure delta A is the average of the direct measure delta A for the A in the capital A. So in this notation, we can write the self-similar measure as infinite convolution. It says that the mu ND is the infinite convolution of the measure delta n to the power minus k times d. Next is that we in this talk we focus on singularly continuous spectral measure. This is first discovered by Jorgensen and Peterson. For example, they showed that the one-fourth self-similar measure mu 402. This measure is a spectral measure, and the spectrum lambda 401 is the set of integers such that if we such that the exponential in base 4 only contain 0 and 1. And also they show that the middle third measure is not a spectral measure. So so there is a question is that for which self-similar measure it's a spectral measure. Next we will introduce a notation of Hadamard triple. It says that net capital N is an integer and BL is a finite subset of integer. And the set B and the set L have the same cardinality. We will say NBL is a Hadamard triple if the matrix 1 over the square root of cardinality B and e to the power 2 pi I B times L over N for B in set B and L in set L. If this matrix is a unitary, we will say that NBL is a Hadamard triple. Here, the Hadamard triple means that actually means that in our notation is that the set L is a spectrum of the delta of the measure delta n to the power minus 1 times b. And also we can check that we can check from the unitary because this metric is unitary. So we can check that if we translate set B or we translate set L, it's also a Hadamard triple. And also we can check from because this matrix is unitary, so we can know that the elements in the set L is distinct modular n. Is distinct modular n. So the cardinality of L is less than capital N. And also we can show that if a set L tilde is equal to the set L in the sense modular n, then the NBL tilde is also a Hadamard triple. So this means that if we know that NBL is a Hadamard triple, we can find many other set L such that NBL can be a Hadamard triple. And it's also very easy to check that the 4 and the set 02 and the set 01 is a Hadamard triple. This is why the one-fourth self-similar is a spectral measure. And there is a very general theorem says that if you given a Hadamard triple, any Hadamard triple NBL, then the self-similar measure mu NB is a spectral measure. The mu NB is the self-similar measure generated by N and the set B here. And this theorem has been extended to Hare dimensions. In Hare dimensions, we can also define define the Hadamard triple and we can consider corresponding self-affine measure in higher dimension. It was shown that if we have a Hadamard triple in higher dimension and the self-affine measure will be a spectral measure. And in our talk, we will focus on in one dimension. And for the singularly continuous spectral measure, there is a very interesting phenomenon which is called a scaling spectral phenomenon. This means that there is some singularly continuous spectral measure. For this spectral measure, we can find a set lambda and also its scaling t times lambda. For these two sets, they are both of them are the spectrum of this measure. But this phenomenon can't happen for absolutely continuous spectral measure. So we can introduce the following definition for spectral eigenvalue. That means if we fix a spectral measure mu, then real number t is called a spectral eigenvalue of this spectral measure if we can find a subset lambda such that the lambda and also the set t times lambda are spectral measure of mu. If this happens, the number t is called a spectral eigenvalue. Another definition is that first we fix a spectral pair mu, and also we fix lambda, the spectrum lambda. Their number t is called a spectral eigenvalue of a spectral pair mu lambda if t times the lambda is also a spectrum of mu. For the second definition, the difference is that we also fix the spectrum lambda, and in the first definition, we only fix the spectral measure, and lambda is just we can just found a lambda, so the lambda is not fixed. So there are two questions. The first two questions is to find all the spectral eigenvalues of a spectral measure. The second is we fixed a spectral pair, mu and lambda, and we want to find all the positive, to find all spectral eigenvalues of this spectral pair. Actually, we just need to consider positive spectral eigenvalue. This is because that it's easy to check that if a set lambda is a spectrum of mu, and then we can know that the minus lambda is also a of spectrum of mu. So we can only focus on the positive spectral eigenvalues. And in our talk, we will only focus on the self-similar spectral measures in one dimension generated by a Hadamard triple mu BL. It means that the spectral measure mu is a self-similar measure mu NB generated by the N and B. Next, we recall some knowledge results for the spectrum eigenvalue problem. For example, if we fix the spectrum pair here is mu 402 and the spectrum lambda 401, we have introduced at before. If for this spectral pair, we have known that for any prime p which is larger than 3, and the p to the power n is a spectrum eigenvalue for any integer n. And also We also consider if we only fix the spectral measure mu for 02, it has been shown that the real number is the spectrum eigenvalue of this measure if and only if t is a quotient of two other integers. So they are give a completely characteristic of the spectral eigenvalues. And there are also many other result about the spectrum eigenvalues for some special case of the self-similar spectrum measure. For instance, for example, when the cardinality of the set B equal to 2 or equal to 3, there are some results to describe the spectral eigenvalues. And also, if the set B is a product from digital set, there are some results. And also there is also some results to consider the spectral eigenvalues problem in higher dimensions, and so on. There had many results about this question, but there is also many questions that are unanswered. So next, we will introduce constructions of spectrum by Zhiqiang and Zhiqiang. We have known that if we have a Hadamard triple NBL and the self-similar measure, mu NBL will be is a spectral measure. And here next I will introduce how to construct a spectrum lambda. Here we assume that the zero is in the intersection of set B and set L. Here, when we given a Hadamard triple, there are two IFS. The first one is generated by N and the set B. The second one is generated by the N and the set L. If a finite set C of a real number is called a circle for the IFS FNL. If we can find the L1, L2, and LK in the set L, such that the tau Li maps Xi to Li plus 1, and for the last one, tau Lk maps Lk to L1. So this is a circle for this. It can be viewed as a periodic orbit in this IFS. And also we called that if a circle called a circle is an extremely circle if the absolutely mbx equal to 1 for all x in the site C. Here, the MB is defined to the average of the e to the power 2 pi I times b times x. Actually, mbx is the Fourier transform of the measure delta b here. And note that we know that the absolutely value of the Fourier transform is bounded by 1. So for the extreme circle, we know that for every x, the absolutely value equal to 1. And because we assume that 0 is in the set L, so it's easy to check that the set 0 will be a trivial extremely circle. So the extremely circle is the set of the extremely circle is non-empty. There is a trivial. And it was shown by Doki and Jurgensen that if we given a Hadamard triple and let mu nb be the self-similar measure, and let the lambda be the smallest set that contains minus c. for all extremely circles C, and also that n times lambda plus set L is a subset lambda. If the lambda is the smallest set that satisfy these two properties, then the mu n lambda, mu n b, and the set lambda is a spectrum pair. Here, uh, uh, this gave one way to construct a spectrum of the self-similar spectrum measure. Here we called this pair mu n lambda is a canonical spectral pair generated by a Hadamard triple NBA. And we also know that the spectrum lambda can be constructed as follows. First, we write D for the greatest common divisor of the set B, and we write the lambda zero equal to the minus of the intersection of K N L intersection Z over D. The KNL is the self-similar site generated by NL, and for this intersection, it can be shown that actually this intersection is the union of all the extreme circles. And if we have defined the lambda zero, then we can define the lambda n to be the n times lambda n minus 1 plus L. Then we can show that the size lambda n is increasing. And then we define the lambda to be the union of the lambda n. And we can show that this lambda is actually, we define we can show the lambda is actually the smallest site satisfy these two properties. So for this lambda, we can show that mu nb lambda is the canonical spectral pair generated NBL. So from this, that we know that if we have if we given a Hadamard triple NBL, then we can know how to construct the spectrum for this self-similar spectrum measure. So next we will we will state our main result. First we fixed Hadamard triple NBL in one-dimensional, and let the mu nb be the self-similar measure. Here we also assume that the cardinality of set B is strictly less than capital N. This is because that if the cardinality of B equal to the N, then the self-similar measure mu nb will be absolutely continuous. But for the continuous absolutely spectral measure, there will the scaling spectrum phenomenon will not happen. So we only focus on the singularly continuous case. So we assume that the cardinality of the set B is strictly less than capital N. So for this self-similar spectral measure, we proved that if given finitely many P1, P2, and PK, and such that PK is co-prime with a capital N, then we can find a set lambda such that P to the power N1, P2 to the power N2, and PK to the power NK times lambda is a spectrum of mu nb for all non-negative integer n1, n2, and nk. So here is that we given finitely integers p, which is co-prime, and we can find a subset lambda such that all the scaling by p1 to the power p to the power integer, all the scaling is also a spectrum of the mu nb. So from this theorem, we will provide the many spectral eigenvalues for the self-similar measure, mu and b. There is a corollary. If we write the set En to be the set of all the positive rational number, which we over U, such that the U, V and U are co-prime with capital N. The set En, it's easy to check that the set En is dense in the positive real number. And by the theorem 1, we can show that any rational number t in the set En where is a spectral eigenvalue of the mu and b. And moreover, we can show that for any finitely many t1, t2, and tk in this set, and the eigenvalue, the eigen subspace, it means that the is a set of lambda such that 0 is in the set lambda, and also lambda and t1 times lambda, t2 times lambda, and tk times the lambda are spectrum of mu and b. For this set, the set of lambda such that this property is infinite. This is just a corollary of our theorem 1. And very recently, our corollary was strengthened by Lu. His result says that we can define the set Q, the set of integer Q, such that NBQ times L is also a Hadamard triple. If we define this set, and we can know that this set T contains all the integer Q such that Q is Q prime with capital N. He shows that the set of lambda such that 0 is in lambda, and also Q times lambda is a spectrum of mu and b. For every Q in capital T, the set of for every Q in set T, and this set have the cardinality of the continuum. In his proof, the construction of the spectrum lambda is more flexible. So he can show that this set have the cardinality of a continuum. But in our proof, we can only show that the set is infinite. Our second theorem is about the spectral eigenvalue of the spectral eigenvalue of the spectral pair. So here we need to assume that 0 is in the intersection set B and set L, and let the mu and BL be the canonical spectral pair generated by the NBL. And then we can show that if the cardinality OB is strictly less than the n to the power 0.699, then there are infinitely many prime spectrum eigenvalues of the spectral pair mu and b lambda. And furthermore, if the cardinality of set B is less than n to the power 1/2, then we can show that almost all prime are the spectral eigenvalues of the mu and b lambda. Here, almost all means that the density of the spectral eigenvalue in the site of prime is 1. So the almost all means that if we look in the density, the density in the set prime is 1. So next we will briefly introduce the idea of the proof for our two theorems. The first there is a lemma which says that if we have a Hadamard triple MBL, and we given a integer which is co-primed with the capital N, then we can know that the MB and the set Q times L is also a Hartmann triple. So this means that we can scale, if we fix MB, then we can scale the lambda with an integer which is co-primed with capital N. And the next we donate the D be the we let the B be the greatest common divisor of the set L, and also we let the mu MB L be the canonical spectral pair. And we showed that if we have an integer which is co-primed with capital N, then the Q is a spectral eigenvalue of the spectral pair mu NBL if and only if the intersection of K and L intersect the intersection of K and L with Z over QD is the same of the with the intersection K and L and the Z over D. Here, the K and L is a self-similar set generated by N and L. The key point here is that we know that Q is co-primed with capital N. Then we know that NB and Q times L is also a Hartmann triple. And from this Hartmann triple, there is also a spectral pair mu N lambda prime. And we can check that Q times the lambda is contained lambda prime. So if we want Q to be a spectral eigenvalue, we only need that lambda prime equal to the Q times lambda. So from this condition, we can check that if we want the lambda prime equal to the Q times lambda, we can check that this condition is equivalent to the condition that the intersection is the same. So there is a key point in this proof for this in the proof for this proposition. So here we know that if we want Q to be a spectral eigenvalue, we need to know the intersection of the intersection of a semi-similar set with some rational numbers. So in order to prove our theorem, we need to recall a result about the rational points in counter sets. Here we given a integer Q is larger than 3, and we also given a finite subset of rational numbers. Here the set A is a subset of rational numbers, and before we can define the KQA to the self-similar set generated by Q and the set A, which is it's a set of sum of AK over Q to the time K, where the AK is in the set K for any K. And also for a P, for an integer P, we also define the DP set to be the union of the Z over P to the power N. Actually, the DP is a set of all the rational numbers that have a finite P-area expansions. And there is a theorem says that if the P and Q and if the P and Q is co-prime, then the set KQA, the set intersection of KQA with the DP is finite if and only if the set the Hausdorff dimension of KQA is strictly less than 1. This means that if the QKA the dimensional is small, and then we know, and also P and Q are co-prime, then the intersection is very small. Small means here we means that the intersection is only a finite subset, is a finite set. Next, we will see how this theorem to applied to study our spectral eigenvalue problem. So we can using this theorem we can prove the theorem one. Theorem one says that we given finitely many p, which is a coprime with a capital N, then we want to find a subset lambda that all the scaling is also a spectrum of the mu n b. To simplify, we just assume that the d is equal to 1. This means that the common divisor of the set b is just 1. And if we give the finite many p1, p2, and pk, we write p to be the product of this p1, p2, and pk, and we know that p is coprime with a capital N. And also we assumed that the cardinality of the set B is strictly less than capital N. From this, we know that the first-order dimension of the self-similar set KNL is strictly less than 1. So we can apply this theorem. So we know that the intersection of KNL and the DP is a finite set. So but if we recall the definition of DP, we can say that the set Z over the power P to the power N, this set is increasing with respect to N. So we can find the N0 such that this finite intersection is actually the intersection KNL with the Z over the P to the power N0. So because this set is because this is because the intersection is just a finite set, so we can find the N0 here. And now we fix the N0, and we also know that because P is coprime with the capital N, we also know that the NB and the site P to the power N0 times L is also a Hadamard triple. And for this Hadamard triple, there is also a spectral pair, which we donated by mu NB and lambda. Here we remarked that this spectrum lambda is generated by the Hadamard triple NB p to the power N0 times L. It's not the spectrum lambda is not generated by the NBL. Next, we can fix any N1, N2, and Nk. So we want that the P1 to the power N1 and P1 pk times P2 to the power N2 and times pk to the power Nk is a spectral eigenvalue, and by the proposition, this is the equivalent to the intersection of the KNP there p to the power N0 times L. For this semi-similar set, the intersection with Z over the P1 to power N1 times P1, P2 to power N2 and times Pk to the power Nk. We need that the intersection of this is the same with the intersection Kn to power N to the Kn P to the power N0 times L with the integer. Here we just apply the probability 2 to the Hadamard triple NB P to the power N0 times L. And if we divide the P to the power 0 from the two sides, we can obtain it's equivalent to the intersection of KNL of this is the same with the KNL with the intersection N over to the power n p to the power n0. But we have known that the intersection, we have known the equality in 6.1 here. Well, and we just need to note that the z over the p to the power n is contained the n to z to the power over the p to the power n, p1 to the power n1 times, and so on to pk to the power nk. And also this subset is also contained in the set dp. So from this equality 6.1, we can show that uh, the equality in 6.2 holds. So from this we can apply probability 2 that the p1 to power n1, p2 to power 2, n2, and pk to power 2 nk times lambda is the spectrum of the mu n b. So from here we have shown that the theorem 1 holds. Theorem 1 holds. So the key point here is we need to apply apply the probability 2 to another Hartmann triple, and we also need the result from the result about the rational points in the counter sets. And also we next we introduce the proof of theorem 2. Here we fix the Hartmann triple NBL, and here we also assume that 0 is in the intersection B and L, and also the cardinality of the set B is strictly less than capital N, and also we assume that N is the D is equal to 1. And also we let mu NB and lambda is a canonical spectrum pair generated by this Hartmann triple NBL. And then we fixed a prime P is larger than capital N. And then we can apply probability that then we will obtain that the prime P is a spectral eigenvalue if and only if the intersection of KNL with Z over P is the same with the intersection KNL with set integer. Here this is because we assume the D equal to 1. So this if we assume that the prime P is not a spectrum eigenvalue, so this equality not holds. This means that we can find a rational number V over P is in the set KNL, where the integer mu, the integer V, such that P does not divide by P doesn't divide V. So if P is not a spectral eigenvalue, we can find the rational number in this form in the self-similar set. Here we also need a result about rational points in counter sets. As before, for Q and subset A, we can define the self-similar set KQA, and every point X in this self-similar set can be written as the sum of the AK over the K to the over the Q to the power over the Q to the power K, and for some infinite sequence AK. And this sequence AK is called coding of X. We have a lemma says that if the Hausdorff dimension of KQA is strictly less than 1, then we can find a constant C such that for any rational number in this set, we can for any rational number in this set, we'll have an eventually periodic coding, and also the periodicalness can be bounded by the C times the U to the power S, where the S is the Hausdorff dimension and the U is the denominator of this rational point. So we can apply this lemma to our rational point mu p mu v over p here. So we can know that the rational number mu and p where v and p over p will have a eventually periodic coding. We donated by L1, L2, Lj, and then the periodic is Lj plus 1 to Lj plus n here, which each Lk in the set L. And also we know that the periodicalness M is bounded by the C times C times P to the power S, where the S is the Hausdorff dimension of the self-similar set KNL. And then if we just write down what the coding means, it means that the V over P is the sum. The first part is just the sum of the LK over the K to the power N, and the second part is the periodic part. Here, this part can be written as 1 plus 1 over the power N to the m and plus 1 over the n to the power 2 times m, and so on. And for these two terms, the sum of the Lj plus Lk over the n to the power jk. And just by a simple calculation, we can show that the sum of this is a rational number with the denominator. The key point here, we need to know the denominator uh, denominator with this rational. We know that the denominator with this rational number is n to the power j and times the n to the power m minus 1. So from this we know that the p is co-prime with v, and also p is co-prime with n, with capital N. So from this we can know that p divide the n to the power m minus 1. So from this we know that the number m is related to the order of n modular p. So we can define we can write the capital P to be the set of prime, and we given an integer, we can define the order of A modular P to be the smallest integer such that n to the power equal to 1 in the sense modular P. So from we have known that P divided the n to the power m minus 1. So from this, we know that the order of n modular p is bounded by m. And we also know that m is bounded by c times p to the power s. So we obtained the upper bound of the order. So to summarize, we have shown that if we have a prime is very large, is larger than capital N, if P is not a spectral eigenvalue, then we know the order is bounded by C times P to the power S, where S is the Hausdorff dimension. This means that if the order is larger than, roughly speaking, if the order is larger than p to the power s, then the prime p will be spectral eigenvalues. So we need to know for which primes the order is very larger. So we define for delta between 0 and 1, we define the set a delta to be the set of all the prime prime p such that the order of the A modular p is strictly larger than p to the power delta. So so we can have the following proposition: if delta is strictly larger than the Hausdorff dimension, and we know that an delta this set is infinite, then we can find a p0 such that if prime in this set is larger than p0, and this prime will be a spectral eigenvalue of mu n b lambda. In particularly in particular, we know that the spectral pair will have infinitely many prime spectral eigenvalues. So we translate the problem into whether the whether we can find a delta which is larger than the Hausdorff dimension such that the site A n delta is infinite. This means that we can find infinitely many primes such that the order of the n modular p is larger than p to the power delta. So we need some results from the number theory. Um, in 1973, adults have proved that for delta equal to one half, for delta in one half, for delta equal to one half, the density of this AA one half for this set, the density in the set of primes, the density equal to one. Here the pi px pi here the pi x is just the prime counting functions. And this theorem, and this result is can be impressed by if we given any epsilon x is if we given epsilon x is a positive valued function, and such that when x tends to infinite, epsilon x tends to 0, we can show that the density of the p the density of the set of the p of prime p such that of the order of A modular p is strictly larger than p to the power plus epsilon p. We can also show this density is also 0. Here is the improve epsilon p compared with the previous result by adults. From this, by applying this theorem, we can show that if the cardinality of B, the cardinality set B is less than n to the power one half, we can show that almost all prime are spectral eigenvalues. And also there is also a result in theorem to we can let the Pn, let the P plus n to denote the largest prime factor of a given integer n. And in 1969, Godford had shown that the set for the set of P, set of prime P, such that the largest prime factor of P minus 1, the is larger than to the power x to the power one half. The density of this set in the set of prime, the density have at least one half. And also this exponent 1/2 can be improved. Up to now, we know that it had been proved by Baker and Hammond, shows that if for the exponent 1.699, we also can show that the density is at least positive. And from this theorem, we can show that for delta equal to 0.69677, the A the capital A delta have the density at least positive in the set of prime. And in particular, we know that the set for the delta equal to 1, 0, for delta equal to 0.677, this set is infinite. So we can apply this corollary to obtain that if the cardinality of the set A is strictly less than n to the power 0.699, then there are infinitely many prime spectral eigenvalues. So so we can prove our theorem 2 by the result in the number theory. So we can up to now we can prove the theorem 2. That's all my presentation. Thanks.
Thank you for this wonderful talk. Are there any questions to Dr. Wang? No question. If there are no further questions, let us thank Dr. Wang again.
Okay.
Thank you, everyone. Yes, thank you, everyone, for joining us today. No question, right? So we look forward to seeing you again in our next
See you
events.
again.
Thank you. Thank you.
Thanks.
Yeah. Bye. Bye, everyone.
Bye.